In the last lecture, we have seen that some statistical techniques for the data analysis, like we have started with the correlation in the data, then we have seen the lines of regression again, and then after that we have seen the curve fitting, how to see whether the data gives you any pattern or not, and what are the patterns that can be. Okay, so first of all, we have seen the regression line, then we have seen if a line can be fitted or not, and then we have seen if we can fit a parabola. Okay, so this was about the data when they are given. Okay, so if I have the data given, then we can think of it. Now we have to see the chances, okay, of happening anything. Okay, so first we need to understand how these are useful in our technology, or why we need to study this kind of topics. Okay, so the important thing is that, for example, we are now communicating over the wireless communication. Okay, over the mobile phones, then internet. We are using Wi-Fi and all. Okay, now the question is, how do we get the messages? How do we get the particular data? Okay, though they travel through lots of channels. Okay, so lots of channels. So, for example, I am sending a message from my Airtel mobile phone to some person. So, mobile phone is in a Vodafone network. Okay, so this message will be transmitted from Airtel, my Airtel number, to the nearest Airtel tower, and then it will be communicated to a central server, and then from that server it will be communicated to the Vodafone server, and then from the Vodafone server it will be communicated to the nearest tower of that person to whom I want to send the message, and from that nearest tower the message will be sent to the person. Okay, so you can see the link, the path of this message. So my phone to nearest tower to central hub, we call it. So from hub to the Vodafone, then hub, and then from Vodafone hub to the tower, nearest tower of the person, and then the nearest tower to the person. Okay, so you can see this is the path of the message that I am sending. Okay, now what are the chances that this message will not be received by the particular person? Okay, so think over it. Okay, what are the chances that the message will not be received by a particular person? Okay, so usually the chances are nearly zero. Okay, usually the chances are nearly zero. I'll repeat my question once again. What are the chances that the message will not be received by the particular person? Okay, so the chances are nearly zero, because when we send a message to a particular person, it is always received. Okay, nearly always received. Okay, so the chances of missing that message are very less. Okay, and now we have to think of this. So that's why what these chances are. These chances are nothing but the probability. Okay, so when we communicate over a network, okay, so there are so many branches in the network. Okay, and moreover, this network may be an open network or it may be a closed loop network. Okay, so the chances that happening a thing, and the chances that happening a favorable thing, okay, this is nothing but the probability. Okay, so now in this unit, in this module, we have to think of the probability. Okay, so we have to think of what are the chances of happening a thing or not. Okay, and this is very useful in the communication networks, in the computer networks, in the analysis. And see, we have a part called minimum, you also might have seen in the discrete structures that or discrete mathematics that we have to find out the minimal path using the Green Big Stars algorithm and then minimum spanning tree for a graph. So actually, what these graphs are, okay? So these graphs are the networks for us. Okay, so for a pure mathematician, it may be a graph, but for us, it is going to be a network. Okay, what network? So our vertices are nothing but the points or the service stations, and then whatever other points we can call them as the clients also. Okay, or another service stations. Okay, and these all service stations are connected, and that gives us a structure we call as graph. And now, if we consider the flow. Okay, so what are the chances that a particular flow will be monitored or it will have a problem? So this and there we need the probability. Okay, so that's why it becomes very essential to understand these things, to understand the probability. Okay, so the base of this is the probability. So if we can understand probability, we can understand these networks in a better way. We can design a network with the minimum error. Okay. And you can understand the example that I started with, sending a message from one service to the another service and one person to the another person who is having two different services. Okay. So this requires to build a network which has the least error. Okay, so least error means nearly zero error. Okay, and if we are able to build networks with the nearly zero error, okay, then that's good. So here we need to understand the probability. So at every point, if the probability is going to be one, okay, then the probability that the person, target person, will get the message is one. Okay, or we are 100% sure that the message which is starting from the source will reach its destination 100%. Okay, so this is the probability of that we need to understand. Okay, and this can be in any problem. Okay, so for example, you are all IT people, so you will be designing the softwares. Okay, or you will be working on the softwares. So when you design a software, okay, so what is the process to get this software in the market? Okay, so first the idea is proposed. Okay, so that means we roughly decide what will be the path of the software. Okay, then the developers, okay, the team of developers will develop that software. Okay, and after they develop the software, it will go for testing. Okay, and the testers will test this software for the dummy data. Okay, and then they will try to extract the information with this dummy data, whatever is there. So, what are the chances that they will get the correct information? Okay, and this decides the reliability of your software. Okay, and that's why when they are very sure that 100% they will get the query or the desired data when asked. Okay, then the software is approved and will go for the sale in market, or will go for the use in market. And that's why here we need to understand the probability of getting the correct data. Okay. So if you are 100% sure, your tester is 100% sure that yes, he is getting everything correctly, then only your software will be approved, and then only it will be open to the market, or it will be given in the market so that it will be sold. Okay, or it will be used. And that's why we need to understand how to calculate the probability. Okay, so some of the basic idea you have for the probability. So first we'll revise that idea you have, you studied, and then we will see some more examples. Okay, so first we need to understand what is the probability. Okay, or what is the formal definition of the probability. So to understand the formal definition of the probability, we need to understand the random experiment. Okay, so as I said, in case of your software, okay, so the tester will put a random query. Okay, that I want this data. Okay, randomly, and then if he is getting this data, then he will say, no, no, I want another data. Okay, and then he will get another data. He will say, no, no, I don't want either of this. Okay, and like that, the software is tested randomly. Okay, and once it is tested randomly, and if it gives all the correct values, then we say it is error free. Okay, error free means nearly zero errors. Okay, and we are most sure means always we are getting the desired data or the desired result. Okay, so that we have to see. Okay, so now let us try to understand the formal definitions of this. Okay, so we'll see the formal definition of probability and the related topics. Okay, so we start with topic probability. Okay, so here we have probability. Okay, now first we need to understand random experiments. Okay, so what is the random experiment we have? Okay, see the basic random experiments are coin tossing and playing that cube. So you play with the dice. Uh, we play Ludo, okay, or we play snakes and ladders. Okay, so what is that die when we throw? We are not sure what will come. Okay, but we know. Okay, what may be the outcome. Okay, so for example, if I consider a coin, okay, so what we have, either we have head or we have tail. Okay, so we know what is the possible outcome. Okay, but what will be the outcome when we toss the coin, we don't know. Okay, and that's why we need to understand. Okay, so this experiment is called a random experiment. When we know the all outcomes, okay, but what will be the outcome in the experiment that is uncertain. Okay, then this kind of experiments we call random experiment. So, what is a random experiment? If we want to summarize, an experiment with the known outcomes but uncertainty in the outcome. Okay, so what we have all the outcomes are known. So, for example, if I toss a coin, then I'll have two outcomes, either it will be a head or it will be tail. Okay, so if I have a dice and then I throw that dice or I roll the dice, then what I'll have if I roll a one die, then I'll have the die has six faces. Okay, so what are the six faces we have? The number one, two, three, four, five, and six. Okay, so we have these six faces numbered from one to six. So when I roll a die, then definitely I know that it is one of these six numbers. Okay, but which is exactly we don't know. Okay, so which is exactly we don't know. Okay, and that's why this is called a very random experiment. So these are some of the standard random experiments we have. Okay, so what we have will define the random experiment when the outcomes are known with uncertainty. Okay, so we have we define the random experiment, an experiment with known outcomes, but each outcome is uncertain. Again, is called a random experiment. Okay, so that's what we have random experiment. Okay, so once we have a random experiment, then we have to think over what is the outcome called. Okay, so we have sample space. So next concept we need to understand is a sample space. Okay, so we have an experiment. So either I'll roll a die or I'll toss a coin. So when I toss a coin, what are the possibilities or what are the um, points or what are the outcomes that I will have? So when I toss a coin, I will have either a head or a tail. Okay, so there are only two possible outcomes: head and tail. Okay, so head and tail, these 2 points form the sample space for this coin tossing random experiment. Okay, now next, if I roll a die, then what are the possible outcomes? So possible outcome is 1, 2, 3, 4, 5, and 6. Okay, so we have these 6 points, okay, which are the possible outcomes. So if I collect all the possible outcomes, then we call this as the sample space. Okay, so what is the sample space? The sample space is the set of all possible outcomes or the collection of all possible outcomes of a random experiment is called the sample space. Okay, so we write the definition of sample space. Okay, so we have the collection of all possible outcomes of a random experiment is called sample space. Okay, the sample space is denoted by S. Okay, so we have the sample space is denoted by capital S. Okay, and now what this outcomes are called. So we have sample points. Okay. So the elements of sample space are called sample points. The elements of sample space S are called sample points, or these are nothing but outcomes of um, random experiment. Okay. So we have the sample space, we have the sample point. Okay, now we have to define a event. Okay, so what is meant by event? Okay, so event means happening a favorable condition. Okay, or in short, a favorable outcome. Okay, so suppose I have tossed the coin and then I want I have to get ahead. So head is my expected point or head is my favorable point. Okay. So I hope most of you have played this game of coin tossing, head and tail. So when you get the desired point, then you win, or if you do not get the desired point, then you lose. Okay, so like that. Then when we ask for head and we get head, okay, then it is an event. So getting a head is event, getting a tail is event, okay, and getting both is also an event. Okay, getting nothing is also an event. Okay, so what happens is, so if I say getting nothing, okay, then this is the event, but it is called as null event. So we didn't get nothing, and that will not happen. Okay, so this is called a null event or impossible event. Okay, so it is a event, but we call it as null event or impossible event because when we toss a point, okay, it will rarely happen that will not get nothing. Okay, so when we'll get nothing, it happens only in movies that the coin is straight. We can say it neither gives you head or it not give you tail. So this is called as impossible event or null event. Okay, but surely it will not happen, and we assume that in our experiments it will not happen. Okay, so this is called a null event. Okay, and then either head you can get or tail you can get. So getting this is a event. So getting either only head is also event. Getting only tail is also event. Getting both of this is also event. Okay, so getting both of this means we say I always win. Okay, so that is the thing. I always win. Okay, so that is also a event. And getting nothing is always also a event. We call it as null event. Okay, so event means the favorable outcome. Okay, so event means the favorable outcome. Getting the favorable outcome is called as event. So let us write the definition of the event. Okay, and then we'll see the different types of the event. Okay, so we have once we have the sample point, then we have next event. Okay, so what is the event? So event means getting the event is defined as the favorable outcomes. Or this way of define sample points. Okay, so if I get the favorable outcomes or the favorable sample point, then we call as event. Okay, so as I said, there are different types of the events. Okay, so what do we have? If I get nothing, then we call this a null event. If I get something, then it is the proper event. If I get all the points, then it is nothing but a sample space. Okay. So now, once I am able to define the favorable outcome, okay, and I am able to define the event, then I am able to define the probability of this event. Okay. So what we have is we want to define the probability now. Okay. So we have suppose let S be the sample space of a random experiment with n of s equal to number of sample points in S. Let A be the event of same random experiment with n of a equal to number of favorable outcomes. These are nothing but sample points of random experiment. Okay, so what we have here, we are assuming random experiment. We are assuming yes to be the sample points, all the sample points in that random experiment, and then we are assuming A to be the event. Okay, so for example, if I consider a coin tossing game, and then what we have uh, suppose we are tossing one coin. Okay, then we will either get head or will get tail. So these are the two sample points. Okay, so head and tail. Then what will have our yes, the sample space. Okay, will have the sample point. Okay, what will be the sample point we'll have? Suppose head for yes for head will consider and T for tail will consider. So our sample space will contain only head and tail. And now I want to define an event. Okay, so for example, I define an event of getting head. Okay, so if I define an event of getting head, then what I'll having the A set will be the set of all favorable outcomes because it is the event. And so the set A will contain H only, and the set yes will contain H and T. And now, if I define the points, okay, so number of points in yes and number of points in A, then number of points in yes is going to be 2, and the number of points in A is going to be 1. Okay, and once I know this number of favorable points and total number of points, okay, then I am able to define the probability of that particular. Okay, so now we have the sample space. Yes, we know the number of samples point n of yes, and then we know an event. So A is the event, and we know the number of sample points in that event. So n of A, and if I know that the number of sample points in yes and number of sample points in A, then we are able to define the probability. Okay, so let us define the probability. Okay, so what we have here, so we'll be having let number of sample points is equal to n. Okay, and number of sample points in A is equal to m. Okay, then what we can say the probability of event A is given as the ratio of number of sample points in event A to the number of sample points in sample space. Okay, so that is S. Okay, so what is the probability of the event A is given as the ratio of number of sample points in event A to the number of sample points in sample space. Okay, the probability of A is denoted by P of A and is given as, what do we have? Probability of A is equal to number of sample points in A upon number of sample points in yes. So it is m by n. Okay. So that's what we can have. So this way we are able to define the probability of the event. Okay. So this is how we are able to find the probability of the event, and this is how we are able to define the probability of the event. Okay. Now, once we know the probability of the event, then what we can have is we can know about this event. Okay. So events may be mutually exclusive. Okay. That is no common point. Then the events may have some common points. Okay. And then in that cases, how we are able to find the probability. Okay. So there are some comments that we need to understand. Okay, for the probability. Okay. So first we need to understand for any event A. Okay. So for every event A. Okay. We have 0 less than or equal to probability of A less than or equal to 1. So probability of A, every event, whatever the event may be, the probability is always in between 0 to 1. Okay. So it cannot be less than 0. We cannot have the negative probability, and we cannot have the probability more than 1. Okay. Now, when we have 0 and when we have 1, okay. So if A is null event, okay. So null event, or we can say impossible event. Okay, so this is going to be impossible event. Then the probability of A is equal to 0. Okay, so when we have the impossible event, then the probability is going to be 0. Okay, then next, when we can say the probability is going to be 1. So if A is equal to yes. Okay, so you can see what we have here. We can say, and this m is less than or equal to n. So if I consider this is going to be 1, so m by n is going to be 1. That means what will be having? This m is equal to n. M is equal to n means what? The number of sample points here in S is same as the number of sample point in A. That means A is equal to S. Okay, so both are having the sample point of same experiment. So that's why they will not have the different points, but they will have the same point. So A and S will have the same point. So if we have A is equal to S, okay, then we can have probability of A is equal to probability of S is equal to 1. Okay, so this inequality that we have seen for 0 less than or equal to A, probability of A less than or equal to 1, then we have when it is 0, if it is an impossible event or null event. Okay, so for example, you are rolling a die and then you ask for 7. Is not possible. Okay, or if you are rolling a die and you ask for 0, it's not again possible. Or if you throw a die and then you ask for the square greater than when the square of a number when a number is more than 3. Okay, so again it is not possible. So that's why these are all impossible event, and the probability of such event is going to be 0. That these events will never happen. Okay. And when we say the probability is going to be yeah 1, so you toss a coin and you say my outcome is either head or tail. So definitely it will be either head or tail, and that's why you are considering all the sample points, and hence the probability of that event will go 1. Okay, so this is how we can have the probability of this events. Okay, now some there are some basic theorems on the probability. So what is that basic theorem? So we can think of the 4. Okay. So if A1, A2 up to AK. Okay. are the mutually exclusive events of a random experiment, then we have summation I running from 1 to k pi is equal to 1. Okay, so how you are able to see this? Okay, so this is your universal set, or this is yes here, and then we have this mutually exclusive events. Okay, okay, so this is event A1, this is A2, and so on. We have this event, and this is AK. So what you can see is, you can see, or the simple for two sets. If I have this is the universal set. Okay. So before generalizing this to many sets, we can think of the universal set is equal to the yes here, and we can have this is A1 and this is A2. Then what we'll be having the probability of yes, or we can have the probability of A1 plus probability of A2. And we know the probability of yes is going to be 1. So it is going to be probability of A1 plus probability of A2. So what I did here, I have generalized this concept here, and then I claim that the summation of all probabilities is going to be 1. Okay, so simple thing, the summation of all probabilities is going to be 1. Okay, so this is in case of mutually exclusive events. Okay, so mutually exclusive means no point is in common. Okay, so no point is in common. So here you can see also no point is in common, and for this all you can see no point is in common. So there is no common point in A1 and A2. There is no common point in AK and A2 and AK and any other set. Okay, and so we can say that if this situation happens, then we can have the summation is going to be 1. Okay, so this is the now what happens if these points are not mutually exclusive? Okay, so we'll see the addition theorem. Okay, so what the addition theorem says that they are simple. Okay, so let A and B be the events of a random experiment. Then we have, okay. So what you can have is so A and B are the events of random experiment. So we can have that this is event A and this is event B. Okay, so we have the T regions here. Okay, and this region is uh, A intersection B. Okay, so this region is A intersection B. Okay, and now I want to find what is the probability of union of this. Means what if my outcome comes in either of these two sets. Okay, so what we can have the probability of A union B. So what are we having? The probability of A. So we have here the probability of A. Okay, plus the probability of B. But when we consider the probability of A and B, okay, so we are considering this region in A also and this region in B also. So that's why what we have to do is we have to subtract this region once. Okay, so we have the probability of A union B is equal to the probability of A plus probability of B. minus probability of A intersection B, because we have considered this region twice. Okay, and that's why once we have to subtract it. So we'll have now this region plus this region and plus this region. So we'll have the probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So these are some basic things that we need to understand about the probability. And I hope you have studied these basic things about the probability in 12th standard. So here up to this is just a revision. Now one more game that is commonly used for the classical probability theory. Okay, so is the playing cards game. Okay, so playing cards. So we need to understand the playing cards. Okay, so how many of you know about the playing cards? Okay, sometimes you might have played it uh, just for a time pass or for fun. Okay, so how many of you know the playing cards? You can unmute yourself and then tell me. How many of you know playing cards? You know Uno cards? How you know Uno cards? Almost everyone. Yeah, Suraj said, you know Uno card or playing cards, normal playing cards, or you know both. So this is also a random experiment. Knowing Uno cards, knowing playing cards, and knowing both. Okay, so it is same as the coin tossing. Okay, so Kalyani knows normal playing cards. That's good. Okay, what about Suraj? You know both or you know Uno cards? Suraj knows Uno card. Okay, that's good. What about Ishika? Playing cards. Okay,
Yes, sir.
Anushka. Srinath, what do you know? Playing cards or Uno cards? Uno cards. Okay.
Uno, sir.
Good. Okay, Uno. Okay. What about Prajwal? Prajwal, which cards you know? Playing cards. Okay. Then can you unmute yourself and then tell me about the playing cards? How many types are there? What are the cards? Okay. So we can use it for our random experiment. Yeah, because there are many people who know Uno cards or might not knowing the playing cards. Okay, so let us know about the playing cards because we are going to use it for our random experiment. See, coin tossing, then throwing a die, okay, and playing cards. These are the three standard random experiments. Okay, because we cannot guarantee. Okay, so that's why these experiments are considered to be a classical random experiments. Okay, and that's why we discuss these three repeatedly. Okay, or we have the combination of these three repeatedly. Okay, so that's why knowing playing cards is important for us now. Okay, so to understand the probability, these are the classical examples. Okay, so Prajwal, can you unmute yourself and then tell me about the playing cards? Okay, anybody who knows playing cards, can you explain me? Or can you tell more about the playing cards?
Sir,
Yeah, who is this?
sir, Ankit.
Uh, okay, Ankit. Yes, Ankit, you unmute yourself and then if you have playing cards, you can show. Okay, or you
No,
can
sir, I
explain
don't
what
have
kind
playing
of
cards.
playing cards.
So there are four
Okay,
types of
but
cards.
you know,
So
good.
there are four types of cards: spade, club,
Yes.
heart, and diamond.
Um,
Each type consists of
okay.
13 cards. Start with ace, then go up to
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then have one joker, king, and queen.
Okay. Yes. Okay.
Uh, Yes, sir.
Great.
That's it.
Right. Great. Yes. Okay. So as the Ankit said, so there are total 52 cards. Okay. So we'll see how the 52 cards look like. Okay. I don't have exactly playing cards, but I'll try to draw it. Okay. So what do you have? See. So we call that there is a pack of this 52 playing cards. Okay. So this we call also as a deck or a pack of 52 cards. Okay. Then there are two types of this cards. Okay. So we have a pack of 52. Okay. Then there are first if we differentiate with the color, then there are two colors. Okay, so one is the red and the other is black. Okay, so we have 26 black cards and we have 26 red cards. Okay, so if I consider this 26, now there are two types of red cards. Okay, so what are the two types of red cards? We have hearts and we have diamonds. Okay, so we have hearts and then we have diamonds. Okay. So we have two colors of this. Okay. So in black, we also have the two sides. So here we have these are 13 cards and these are also 13 cards. In black, okay, we have clubs and spades. Okay. So the clubs we have. Okay. So this is clubs. Okay, and then spades we have okay 13 cards of spades. Okay, so these are spades. So 13 cards of each of this set. Okay, so we have 13 card of diamond. We have 13 card of hearts. We have 13 cards of the clubs, and we have 13 card of spades. Okay, so here we have 13 cards. So this way we have the four sets of each of this type. Okay, now in each set of 13 cards, okay, what we have is we call it as 1, then 2, 3, and then we have up to 10. Okay, so 4, 5, 6, 7, 8, 9, and 10. Then we have Jack. Okay, then we have Queen, and we have King. Okay, so here in this 13 cards, again, so we have there are two types of cards again. So from 1 to 10, okay, we consider these as number cards. Okay, so these are the number cards because we have 1 to 10, and the another set of the cards. Okay, this we call as picture cards, or these are also called as face cards. Okay, so either we have the picture card or we have the face card because we have faces for these cards. Okay, or we have pictures for this card. Okay, so this way we have a pack of 52 cards, 26 red, 26 black, then 13 hearts, 13 diamonds, and then we have the 13 clubs and 13 spades. Okay, and we have the face 13 cards. Each card contains number card and then the picture card. So what we have, if I consider the 52 cards, then I have 40 plus 12. Okay, so these are the number cards and these are the face cards. Again, so this way we have a pack of this 52 cards. Okay, so these are the basic things. And now we know the another game, as I said, the coin tossing. Okay, so what we have, any coin, if I toss, I'll have head and tail. Okay, so only two outcomes. So sample space for this coin tossing is yes. Okay, sample space for this experiment is 52 cards. Okay, sample space for coin tossing is head and tail. And if I consider rolling die, then sample space. What is the sample space we have? 1, 2, 3, 4, 5, and 6. Okay, so this we usually use for the game Ludo, snakes and ladders, and like that. And this is a simple coin tossing head and tail. Okay, so these are the three classical examples. Okay, to understand the probability. So this is the first example. Then second example, okay, is the coin tossing, and the third example is the rolling up die or playing Ludo. Okay, so these are the basic experiment that we have. Okay, so do you have any doubt up to this, or basically you know all these games? Okay, so in Uno cards also, if we consider, then there are the different types of cards. First, there are the number cards. Okay, but in Uno you have zero. Okay, in playing cards we don't have zero. Okay, so in Uno we have 0 to V10 we have, and then after that we have the color change card plus 2 card plus 4 card. Then we have the backflip, reverse, okay, and so on. So we can analyze the number of cards. Okay, but in Uno cards the number is more. Okay, so that's why we limit ourselves to playing cards. So which is 52. Easily we are able to do the calculations on this using calculator. Okay, but if we go for the Uno card, may possible your calculator will not able to do it. So if you want to check, then check 80 factorial. Okay, so calculate 80 factorial on your calculator and then see what happens. I hope it is the number 80 factorial. If now they have increased the capacity of calculator, then it may be more. Okay, but usually your calculator is not able to calculate more than 80 factorial if it is Casio 991 MS. Okay, so that is. So do you have any doubt in basics? So today we have seen the basics of probability. So is there any doubt whatever we have seen up to yet? So do you have any doubt up to yet whatever we have seen? Okay, no doubt. Good. Okay, that's great. So no problem. Okay, these are the basics that we have revised today. Okay, so we'll see more example.